Hello, this is another video about protection. And in this video, I would like to talk about relay coordination using time over current relay model. I think we don't need to waste our time on modeling of our network system anymore, because we discussed a lot in the previous videos. So I already prepared a 5-bus network system which connected with short overhead transmission lines and powered from an external grid. To minimize and isolate the faulted region from the healthier part of our network system, we need more than one protective devices. Therefore, I am going to install 4 protective relays in series with certain characteristics, and each of them should provide a specified operating sequence. In case of fault or overload objective, only one relay operates to clear the fault, and the other relays are aware of the fault. In such condition, different timing should be used to determine which device cleared the fault. So the application of this timing scheme is called coordination. So let us learn it step by step through working on our project in PowerFactory software. Before installing the relays, we need to import the relay models, if we cannot use relays from the global library of DIgSILENT. If the models of your relays existed in the global library of DIgSILENT, you don't need to import them from the outside. Since I use KCGG relays, fortunately it is existed in the global library of DIgSILENT. So we are happy and we don't need to import any other relay models. So now let us install relays on this switch symbol next to bus bar 1, 2, 3, and 4. Right click on this switch symbol next to your first bus bar. Select new device, and before implementing the relay model, we used to create CT or current transformer, as we discussed in the previous video. So let us first create CT for all our switches, then implement our relays. Click on current transformer and create new project type, name it CT1. Then set the primary tap to 100 ampere and secondary tap to 1 ampere. Click OK. And do it for the second, third, and fourth relays with the same ratio of primary or secondary current values. So the installation of CTs are completed. Now let us implement our relay model. Again, right click on the first switch. From new device, choose relay model. Then select global type. From relay library, click on overcurrent relays. Then click on GE LSTOM, then click on KCG series and choose KCG 142 1 ampere. Click OK. Now our relay model is installed. And here you can notice all the slot definition and also some multiple setting groups. For example, these are the three phase elements for inverse and definite time characteristics. And these are earth fault elements and their respective time delay. Let us determine the rating and settings only for the first stage, inverse over current relay. This is the first stage, this is the second, and this is the third stage. Double-click on the first stage and change characteristics to standard inverse. Enter 3.20 secondary amperes for current setting and 0.35 seconds for time dial. Rating of current setting is the same for all relays, but time dial is changing. It decreases as moving farther from the source, since the magnitude of the fault current decreases as the fault moves away from the source. So we need to decrease only the time dial for the remaining relays as going downstream or moving away from the source. Click OK and make all the other elements out of service except current transformer and trip logic. So let us name it R1 and click OK. Coming to the second relay, the same as relay 1, current setting is 3.20, but decrease the time dial to 10%. Click OK. Make the other relays out of service similarly as we did in the first relay setting. Name it R2, click OK. Similarly, do it for the third and fourth relays by decreasing 10 or 15% time dial based on characteristics of your network system. The relay settings have been completed. Now let us create time over current plot. Start from the first relay, right-click, select time over current plot. Now an inverse time over current curve is created, and the operating time for a protective relay is inversely proportional to the magnitude of overcurrent. As you can see, for a slight overcurrent, a long time is required for the protective device to operate. As overcurrent increases, the device operation is getting faster. Also, let us add time over current plot of the other protective relays. Right-click on second relay, and this time we do need to create a new time over current plot. So add to time over current plot. Similarly, do for the third and fourth protective relays. Now you can see all the inverse or current relay curves. As we expected, the fourth relay has the lowest time level setting, while relay 1 at breaker 1 has the largest time delay and will not trip unless none of the other breakers trip. When a fault occurring at bus 5, the fourth relays must operate and switch at bus 4 must be open for this fault condition. But the third, second, and first relays will also sense the fault, but it will not trip, because the time dial setting of this relay will be faster comparing to the upper relays. For better understanding, let us apply fault at every buses. But before that, take a simple load flow calculation. From the graph, you can see that none of our relay is tripping, so there is not any problem with our system. Apply fault at bus 5 to see the fault clearing time at each buses. If you put the cursor on the result box, you will notice initial short circuit power, initial short circuit current, and peak short circuit current. But fault clearing time is not shown. Let us add it. Right-click on the result box, select Edit Format for Edge Elements, create append rows, double-click it, and select TFCT, Local Bus Fault Clearing Time. Click OK. Now let us check it. Fault clearing time at this bus is 0.199 seconds, and at this bus it is 0.298 seconds, and this bus it is 0.497 seconds, and at this bus it is 0.696 seconds. So the fault clearing time, as you have seen, is increasing as we move upstream, close to the source. If you go to the time over current plot, you can see from here the same fault clearing time. Next, verify the fault at bus 4. You can see that for this fault, this relay is not tripping, because the relay is after the bus. So the relay will not see the fault at all. That is why it is not tripping. but this relay can see the fault, and the fault clearing time is 0.298 seconds. For this relay it is 0.497 seconds, and for this one it is 0.696 seconds. Let us apply a color shaping for our single line diagram to see all relays in different color. So from diagram coloring, select secondary equipment, and from here select relays, current and voltage transformer. In preview, the relays are presented in red, current transformers in green, voltage transformers in black, and instrument transformers in brown color. Click OK. Now you can see that all relays are colored. So we verified the fault at bus 5 and 4. And similarly, you can check fault current, tripping time, and the relay tripping time for bus 1, 2, and 3. We can conclude that the relay farthest from the power source has minimum fault current value, and the time delay decreasing. It is important to assure that the downstream relay is able to clear the fault before the upstream relay begins to trip. The next thing that I am going to tell you is how to apply the grading margins. It is very important for the coordinating. As you noticed, when we applied the fault at bus 5, more than one relays were contributed to the fault. So that may create a problem to determine the location of fault. To avoid such a condition, we need relay time grading margin. The grading margin is actually the time interval between the operation of two adjacent relays. If it is not provided, more than one relay will contribute for a fault, leading to difficulties in determining the location of the fault. Let us apply it. Double-click on time over current plot. Click on the options. In the options, you can see the grading margin down here. Let it change to 3.4 seconds, and from display automatically option, select current and grading margin, and leave the other settings as they are. Click OK. Calculate short circuit at bus 5. Now you can see the time grading margin as well. For example, the time grading margin between relay 5 and 4 is 0.099 seconds, and between relay 4 and 3 it is 0.199 seconds. Also 0.199 between relay 2 and 1. Okay, so far we learned the coordination and the relay time grading margin. Here, as you can see, they are inverse time over current curve. So you can also combine them with instantaneous or definite time over current curve, as we did in the previous video. Let us do one of them as an example. Right click here and click on Edit Device. Then double click on your relay. Then double click here and make it in service. Assume 10 second ampere for pickup current and 0.4 second for time setting. Click OK. If we check our curve, you see that the second stage definite time or current is operating after 10 secondary ampere or 1000 primary amperes. Similarly, you can combine it for the other relays as well. To see the output of your protection setting, from Change Toolbox, select Protection, then click on Output of Protection Setting, mark Instrument Transformers and Overcurrent Protection. From Protective Device, select All Devices option, then execute it. This is your relay setting, and you can export it as HTML or Excel. That is all for this tutorial. I hope it was helpful and easy to follow. If you found this video useful, then please like the video. Also subscribe if you haven't done yet. Thank you for watching the video and see you in the next video.